Um, Okay, awesome. So a little bit about how this class works. So fundamentally, I think it's really important that you guys understand like concepts and examples. So I don't give you random formulas to memorize. I don't give you random techniques to memorize. I give you guys lots of different problems so that way we can work together and you get a feel for how to apply different concepts in different scenarios. So to start off, we're just going to do a little bit of warm up, a little bit of creative thinking to get ourselves in that kind of mindset. So I want to give you guys kind of a little bit of a brain tease here, okay? So let me give you three consecutive numbers. I'll give you guys 3, 4, and 5. Can you find the product of 3, 4, and 5? Okay, perfect. Algebra, so many people saying it is 60. Absolutely correct. Okay, now can you tell me what 4 cubed is? What is 4 cubed? Yeah, 64. Okay. Cool, cool. So you might be like, okay, why is she making me multiply all these numbers together? Why is there a 4 cubed? Okay, maybe you don't see anything just yet. I mean, I don't see anything interesting here. So let's look at something else. Let's do 4 times 5 times 6. What does that equal to? 120. Very good. And what is 5 cubed? Okay, Divion sees it. All right, 5 cubed is 125. Perfect. Okay, and Divion said he saw it, or said they saw it, but maybe you still don't see it, and that's okay. So let's step away from the threes and the fours. Let's go to something else. Let's go to 9 times 10 times 11. What does that equal to? 990. Very good. And what is 10 cubed? 1,000. Excellent. Okay, I think a lot more of you guys are able to see this pattern, so I'm gonna have one of you guys share this pattern with me. Let's see. Does anyone want to raise their hand, unmute, share what they see? Okay, I see Manit's hand up first. Awesome. Manit, do you want to go ahead?
So for the 3 times 4 times 5 example, since 4 cubed is 64 and 3 times 5 is 15, so basically it's 1 less than 4 to the power of 2. So basically we can just, it's 64, which is 4 to the power of 3 minus 4, which equals 60.
Oh, awesome. Okay, that's perfect. And then Divyan, did you see the same thing? Was that the same pattern that you saw? Yes. Okay, awesome. Yeah, and that's absolutely correct. Okay, so if you take a look at 120, if we do 5 cubed minus 5, we get 120. And if we look at 990, that's just 10 cubed minus 10. And so you must be like, wow, that's pretty neat, pretty coincidental. Like, how did she just know it was the middle cubed minus the number itself? Well, we can actually do a little bit of an algebraic proof with this. So to start off, I want to get you guys in this kind of thinking. How can we generally show that this is true? Well, we can do a little bit of algebra. So to start off, let's say that we have a number n, then we have another number, n plus 1, and then we have another number, n plus 2. That's how we show these numbers are consecutive. And that was kind of the rule we had here. These numbers had to be consecutive. So I want to multiply all of these together. Now, when I multiply these together, what should I get? What do you guys think? If you need pen and paper, use that, because this can be a little tricky to do in your head. Okay, Manit, check your work. You're close. You're very close. You just missed one term. Actually, there shouldn't even be a minus n term, considering that. Yeah, there you go. Yeah, yeah, yeah. Good, good. Okay, so if we take a look, first we have n. If we first multiply these first two terms, so this term and this term, we get n squared. Actually, you know what? That's a little unnecessary. You know what we could do instead? Hold on. Let's multiply these two terms. It's probably better to do that. Okay, so if we start by multiplying those two terms, I'm sure all of you guys are familiar with FOIL, but just in case you're not, I'll walk through it really quickly. We'll do the first terms first, so n times n is n squared. Then we'll do the outer terms. So n times 2 is 2n plus the inner terms, which is 1 times n. So in total, you get 3n. And then you multiply the last term. So 1 times 2 is 2. And then we have that n term. So in total, we get n cubed plus 3n plus 2n. And that's it. So some of you guys are pretty close. A couple of you guys, make sure to check your work. Oh, actually, hold on. I missed a square term there. Yeah, so Arav, that's absolutely correct. Manit, check your n plus 1 cubed minus n. You're missing like one term, I think. And then also Arav, or not Arav. Yeah, I think that's it. Okay, cool. So we can write this. I really like where most of you guys are going with this n plus 1 idea, right? Because if I say n cubed and I say 3n squared, I'm pretty confident like this is somewhere around n cubed, like some kind of cubic, right? So actually, a really important cubic for us to know in algebra is n plus 1 cubed. And we'll talk a little bit about how we can arrive to like what n plus 1 cubed is. Actually, if you want, you can multiply it out yourself. But we do get n cubed plus 3n squared plus 3n plus 1. So can you guys tell me the difference between this term and this term? What's the difference? I think Manit has it in the chat. Thanks, Manit. Anyone else? You guys got any ideas? What's the difference between those two expressions, those two cubics? Yeah, 2n and 1. Absolutely correct. So we have an extra 2n term, or we have 2n, and we should have 3n. So to get an extra n, we would have to add an n. And there is no constant term here. It's just 0. But we have a constant term of 1 here. So to account for that, we would add a 1. Thanks to Rob as well for putting that in the chat. So in total, we're missing an n plus 1 difference. So really, we can write this expression as n plus 1 cubed minus n plus 1. And so that's how we're able to get all of these things over here. Because if you look at it, n plus 1 is the middle term. So we're doing the middle term cubed, and then we're subtracting that middle term. So in this case, I have 5 cubed minus 5. In this case, I have 10 cubed minus 10. So in that kind of fashion, we're able to kind of notice a pattern originally and then go in deeper and prove it generally. And so that's a big thing in algebra. What we're really trying to do is we're looking for random patterns that we see, and then we're trying to prove them algebraically using maybe variables, maybe setting up systems of equations, things like that. So this is kind of like a theme of our class. We're going to do lots of different problems, and then we're going to prove generally that a lot of these different things work. So that's just a fun little trick. Maybe it's a cute little thing if you guys are still doing like number senses and stuff, maybe that pops up. Okay, awesome. So I want to dive into a little bit of review. So starting off with order of operations, I think a lot of you guys are already familiar with this. Hopefully you are, because it's a very important idea. But just in case you need a little refresher, we'll go ahead and do that really quick once I minimize this. Okay, awesome sauce. Okay, so with order of operations, I'm sure you've all heard the acronym PEMDAS, or PEMDAS. And so PEMDAS is basically, okay, well, actually, I can write this out. So there's a couple of ways to kind of go about this. So we have PEMDAS. And so a lot of people remember PEMDAS as please excuse my dear Aunt Mary or dear Aunt Sally. And so basically what each of these, what the acronym stands for is the order in which you should kind of calculate an arithmetic operation. So P is for parentheses. What is E for those of you guys who are like whizzes at PEMDAS? What is E in PEMDAS? Exponent. Awesome. What about M? Oh, Karthik's got the full thing out there. Thank you, Karthik. And thanks everyone else as well for putting in multiplication for M. Multiplication. Awesome. What about D? Division. Very good. And A? Addition. Good. And S? Subtraction. Very good. Yeah, that's absolutely correct. So, it's not very difficult to remember this. It's also not very difficult to apply, but there are definitely some pitfalls where people get mixed up. So it's really important to have parentheses and expressions because otherwise it's very easy to get confused. You always want to make sure you're writing your parentheses. But let's go ahead, practice a couple of examples and see how good you guys really are with PEMDAS. So actually, before we do that, a couple of key things I want to bring up so we avoid mistakes going forward. You always want to start with the innermost parentheses and then work your way outwards. That way you're evaluating as you go. Multiplication and division are kind of on the same level. Mostly we just work like left to right for this. So left to right. So whichever comes first, we address. The same goes for addition and subtraction. We kind of just go left to right. Okay, awesome. So let's start simple and then we'll get a little bit more complex. So what is 4 plus 3 times 2? What do you guys think that is? Good, it's 10, yeah. And so the way we can get that is first we look at multiplication, so 3 times 2 is 6, and then we add that to 4 to get 10. Now, what if instead I had done parentheses here? What does that give me? 14, good, because I'm evaluating parentheses first. So 4 plus 3 is 7 times 2, which gives me 14. Very good, awesome. Okay, now let's say I had instead done 5 times 2 plus 3 squared. What is that? 125. Good. Thanks, Karthik, Manit, Divyan, Lorena. Wow, so many people. Thank you, guys. Awesome. So, yeah. So we start off with our parentheses. 2 plus 3 is 5. Then we go to our exponents. 5 squared is 25. And then we multiply again by that 5. So that gives us 125. Awesome. Okay, now let's say I had maybe erased these parentheses. What would I get instead? I guess I can move this 2 over here. See, oh, now we get some differing examples. 13, 19. Okay, okay. Um, I see 19 predominantly. So let's look at that. So first we start off with those exponents because exponent is more important than multiplication. So we go with 3 squared, which is 9, and then we add that to 10 to get 19. Okay, very good. Awesome. All right, now what if we had instead done, let's see. Oh, there we go. All right, what about 12 divided by 3 plus 2 times 4 minus 1? This is kind of just like a number soup, so be very careful. All right, I see a lot of people saying 11. Okay, so first we're going to start off with that division because even though, or yeah, we just start off with the division in this case since they're the same level. So 12 divided by 3 is 4 plus, then we take care of this 2 times 4, which is 8, and then minus 1, which is equal to 11. So notice how we didn't do like 4 plus 2 times 4. That's because this addition is lower in precedence than the multiplication. So we do 2 times 4 before we do any kind of addition or subtraction. So that's pretty important to remember. Now, if instead, let's say I had done this, what would I get? Rod, check your work. Yeah, good. I would get 23, and that's because I do 12 divided by 3, which is still 4, but now I'm adding that 2. So then I would get 6 times 4, which is 24, minus 1, which is 23, like most of you guys are saying. Awesome. All right, and then let's do another one. This one's pretty easy because I'm giving you guys kind of like the notation so you don't make any mistakes, but go ahead and let me know what you guys get. Hanukkah, check your work. You're close. I think you just missed one last step. Yeah, okay, I see a lot of people saying 4, and that's absolutely correct. Now, the reason why that is because we do 3 times 2, which is 6. So 6 plus 6 is 12, and then I divide that by the 4 minus 1 in the denominator, so 3. So 12 divided by 3 is indeed 4. Okay, awesome. All right, let's do a couple of trickier ones. Or actually, what can we do? Okay, yeah, we can do 2 plus 3 times 4. What is that equal to? Yeah, 14. Yeah, because 3 times 4 is 12, plus 2, 14. Excellent. Now what about 2 plus 3 times 4? 20. Good. That's because 2 plus 3 is 5, times 4 is 20. Now, I'm sure a lot of you have already learned about the associative property and all that jazz, which is wonderful, but you have to be careful whenever you're regrouping your parentheses, because as you can see, if I do parentheses around 3 and 4, that's not the same as me doing parentheses around 2 and 3. And the reason why that is because my operations are different. If they had both been addition or they had both been multiplication, it would be fine if I group my parentheses differently, but because they're different operations, I have to keep my parentheses, like I have to be aware of my parentheses. So that's a pretty important idea to remember. Okay, let's see. All right, what if we did 6 plus 4 divided by 2? What is that equal to? 8, good. So a lot of people will actually say 5 because they do 6 plus 4 divided by 2. So 6 plus 4 is 10, divided by 2 is 5. That's what they'll do instead. But remember, we don't do arithmetic in the order we see it. We do it using PEMDAS. All right, and then one final thing. Let's say we did 8 divided by 4 times 2. What is that equal to? 4. Very good. Okay, so this one confuses many people. They actually think it's just 1 because they just do this 4 times 2 first, thinking that multiplication always comes before division. But remember, multiplication and division are on the same level. So if you see division first, you use division. If you see multiplication first, you use multiplication. So in this case, I see the division first. So I do 8 divided by 4 to get 2, and then I multiply that by the other 2 to get my final answer of 4. All right, I think you guys are doing really great with this. Let's do a couple of harder examples and then we'll move on. So I'm gonna kind of minimize this. I'm thinking about the best way to do this. Okay. All right, awesome. I'll leave those couple of examples up there just in case you guys want to think about anything. Okay, so let's do 2 plus 3 times 4 minus 1 squared divided by 6. So lots of letter soup once again, but I think you guys have got this. All right, don't forget PEMDAS. That is the golden rule in these kinds of questions. I'll write it up here just in case. Okay, Pranay says 6.5. Okay. Oh, that's a plus sign. Sorry. Yeah, if my writing ever gets like really confusing for you guys are welcome to tell me that it's very bad. Okay, cool. Yeah, Arena, Nishala, Ditya, I'm seeing all your answers now. Arush, awesome. Yeah, it is 6.5. That's absolutely correct. So once again, we start with the parentheses. We get 9. Then we do 9 divided by 6 because that division we see first. So 9 divided by 6 is 1.5. So we do 2 plus 3 times 1.5, which is 2 plus 4.5, which is 6.5. Okay, this one's a little trickier because you start seeing decimals and you're like, oh gosh, that's pretty scary. This one's it's not terrible though, I promise. It's not too terrible. Okay, the nice thing is that at least it's not like an infinite decimal or like repeating. It ends. Yeah. Okay. All right, let's do 6 times 4 minus 3 plus 2 divided by 2. What do you guys get for this one? Okay, Arunya, check your work. Varad, Manit, I actually agree with you guys. Yeah, it is in fact 22 because we do 2 divided by 2, which is just 1. So 6 times 4 is 24 minus 3 plus 1, which is 22. Very good. So if any of you guys have ever played the game where like you have to make 24 and you have to use like 4 numbers in a bunch of different orders and parentheses and stuff, PEMDAS is a lot like that, right? Because you're trying to pick out the best operations and the right order of parentheses and stuff so that you can get like the number 24. So that's how I like to think of PEMDAS. If you guys have never played the game before, I recommend you check it out because it's actually pretty interesting. It's also very hard. It's harder than it seems. Um, yeah, it's a very good application of PEMDAS. Okay, awesome. Alrighty. I think you guys are doing really well with this. So we're gonna move on to our next topic. And if we have time, maybe we'll come back, do some maybe 24 questions. But we'll see. Okay, awesome. Alrighty, let's take a look at exponent rules. So exponents are a really, really big part of algebra. I mean, we've talked a little bit about some exponents already, but that's only like how to calculate exponents. There's a lot of other rules that are involved. So it's important that we understand that because it shows up all the time, just everywhere. Okay, so let me go ahead, clear my screen. Okay. Perfect. Alrighty, so let's first start off with something pretty simple. We're gonna start off with the product rule. And actually, when I'm introducing a lot of these rules, I think I'm gonna do more examples, so that way you guys are able to visualize all these things and the variables. So let's first start off. If I do, let's do 2 cubed times 2 to the 4th. What do I get? Okay, Manit says 128. Perfect. Yeah, and I really like what Divion said. That's actually 2 to the power of 7. That's absolutely correct. Yeah, that's pretty interesting. Okay, now let's say I did 3 squared times 3 cubed. What is that? Yeah, 243, which is 3 to the 5th. Okay, I'm trying to get numbers that are small enough, but so far all of these numbers are one apart. So you must be thinking, okay, maybe this only applies for numbers that are one apart. Well, let's say I did 2 squared times 2 to the 5th. Oh, wait, hold on. Let's do 2 to the 6th. There we go. What is that? 256. Thanks. And Kenzo, thank you so much for 2 to the power of 8. That is absolutely correct. Okay, do you guys see a pattern? Is there anything to see here? What do you guys think? Yeah, Manit says yes. Vivian says you can add the exponents. Kenzo says yes. Awesome. Pranay says add exponents. Radhi says yes. Okay. Perfect. Oh, I really like what Nahira says. Bases of the same powers have the exponents added. That's really important. Let's talk about why. So I can express my base. So in an exponent, I have my base. In this case, for 2 cubed, my base is 2. And then I have my power or my exponent. So that's the thing that's on a higher level, so exponent. So if my bases are the same, you'll notice in all of these examples, I have 2 and 2, 3 and 3, 2 and 2. So I'm never doing anything like 2 and 3, right? Because if I do that, I cannot use the product rule. So let's actually formally express what the product rule is. Let's say I have one exponent, a to the power of m, and I have another exponent multiplied by another exponent, a to the power of n. Actually, you know what? M and n are hard to say. I think I'll do p and q. That's easier. Okay, times a to the power of q. So in total, what is a to the power of p times a to the power of q? What does that come out to be? A to the power of p plus q. Perfect. Yeah. So as you can see here, for all of these questions, if you notice, 7 is 3 plus 4. 5 is 2 plus 3. 3 and 4, 5 is 2 and 3, and 8 is 2 and 6. So it's really interesting. We're able to add these exponents together to get this term over here. And so the reason why we can't do like 2 cubed times 3 to the second, you can't add these exponents together, right? Because what would you do in this bottom part? Would you do 2? Would you do 3? Would you do 2.5? Like you don't know. So we're not able to multiply or form, we're not able to consolidate like two numbers with different bases. Yeah, I see a lot of you guys multiplying this out to 72. That's correct. That's actually a prime factorization of 72. But we can't express that in any other kind of base form. Okay, cool. I think that's important to remember. Alrighty, so I'm sure you're like, okay, there's a product rule. Is there not a division rule? There is, but we will come back to that. because I think there's a couple of things we have to talk about to build up to the quotient rule. Okay, let's talk about the power rule. All right. So if I have, actually, let me move this over really quick. Okay, so let's say I have, let's do two. Well, twos are easy to do because it's easy to calculate their values. Let's do 2 squared and then cube that. What is that equal to? 64. Good. What is 64? Can 64 be expressed as a power of 2? Yes, it's 2 to the 6th power. Good. Thank you, Vivian. And thank you, Aditya and Ahanika. Perfect. Yeah, it's 2 to the power of 6. Perfect. Now, let's say I did 3 cubed, and then I squared that. Now, this one might take you guys a couple seconds to figure out, but that's okay. Take your time. Yeah, Manit, it's 7:29. Thank you so much. I don't know if you had that memorized or if you did that really fast. Thanks Serenia and Hanukkah as well, and Aditya. And I think someone above, I think it was Vivian, said that this is 3 to the power of 6. And I wholeheartedly agree with that. And I think a lot of you guys already saw the rule here, but just in case, something important to note is when you raise a power, an exponent, to another exponent, what do you guys do to both exponents? What am I doing here? How do I get 6 from 2 and 3? Yeah, I'm multiplying. Thanks, Arush. Yeah. So if I have like an exponent, we can say a to the power of m, and then I raise a to the power of m to the nth power, that's going to be a to the power of m times n. And so you might be wondering, like, okay, maybe it's just a coincidence it worked out like that. I mean, she did use a couple of 2's and 3's at the same time, but let me show you why this actually works. So if I have 2 squared, that's 2 times 2, right? And then I'm cubing that. So this is equal to 2 times 2, and then multiplied by 2 times 2, and then multiplied by 2 times 2. So how many 2's are by multiplying in total? How many 2's would I multiply in total? 6. Perfect. That's because I have 2 2's, and I'm adding together all of those 2's. So this kind of is based off of this rule over here. This is 2 to the power of 6. A really good thing to remember is that exponentation is repeated multiplication. And when I'm doing multiplication, that's just repeated addition. So if I'm multiplying 6 2's in a row, that means that's 2 to the power of 6. So as you can see, it's very much easy to see how if I'm raising an exponent to another exponent, I'm just multiplying those exponents together. All right, how do we feel about that? Thumbs up, yes in the chat, smiley faces. Okay, thumbs up all around. Does anyone have questions at this point? I know we have done a lot of different concepts and stuff, so if there are questions, feel free to message me, raise your hand, whatever you need to do, and I will answer those now. Okay, awesome. It seems like everyone's doing really great. Okay, excellent. All right, so let's move on from here. Okay, I'm gonna skip around a little bit. Let's do negative exponents. Okay, I think this is pretty interesting. I'm gonna have to minimize this a little bit. Oops. Oh gosh. No, my tablet is really acting up today. Okay, there we go. All right, I like this purple color, so I'm gonna use that now. Alrighty, so let's say I have, okay, we worked a lot with positive exponents, right? We have 2 squared, you have 5 to the 4th, we've done a lot of positive stuff. Now let's say I had a negative exponent. Let's say I did 3 to the negative 3. What could that possibly be? What do you guys think? Okay, Manit says negative 27. I think that's a pretty good guess. Does anyone have any other guesses? Okay, wow, it seems like we all think that 3 to the power of negative 3 is negative 27. Well, I am sorry to say that it is actually not. Now, oh, okay, and actually Rob has the correct answer, so if you guys want to take a look at that. Yeah, all right, so let's take a look. I think this is pretty interesting. So, what is negative 3 cubed? What do you guys think that is? Yeah, that's negative 27. So there's a difference between those two. Now, if I'm doing something raised to the negative power, I'm doing a fraction. So negative exponents are how we represent fractions. So if I do 3 to the power of negative 1, that's 1/3. Now, if I do 3 to the power of negative 3, that's 1/3 cubed, which is just 1 over 27. So that's what a negative exponent does. Now, if I like do an exponent with a negative number, so if I do like a negative number raised to some power, now that value will depend based on the power. So if my power is even, I'll obviously get a positive number, but if my power is odd, I'll get a negative number. So once again, to repeat, 3 to the power of negative 3 is actually 1 over 27. So that is the correct answer. Okay, awesome. So now that we have negative exponents, I want to ask you guys about some division stuff. So before I mentioned like, okay, we have a product rule, there's got to be a division rule, but I said I wanted to wait a little bit. So I waited long enough. So let's go ahead, take a look at what this division rule could possibly be. All right, let's say, I'm going to make this a little smaller as well. Okay. Okay. Um, let's say, right. Actually, let me use a green. Okay. So let's say we have 3 to the, actually, you know what? I'm getting kind of bored of threes. Let's do fours. Let's say we had 4 to the power of 6 divided by 4 to the power of 2. What is that equal to? Okay, I see 4 cubed, 64. I also see 256. Do I see any other answers? Does anyone have something different from these two? Okay, no different answers. Cool, cool, cool. All right, what about, let's do 5 to the power of 7 divided by 5 to the power of 5. What could that be equal to? 25. Very good. And I think a lot of you guys are already seeing the rule and the pattern. But in case you're not, that's totally okay. We'll go into what the rule is. So what did we say about fractional exponents? Or not fractional exponents, about fractions. How can we express a fraction? As a negative exponent. Very good. So if I have something like a to the power of p divided by a to the power of q, how can I write a to the power of q? What can I express that as? What do you think? 1 over a to the power of q. Generally, what would that be? Think about what we did over here. A to the power of negative q. Very good. So this would be a to the power of p times a to the power of negative q, right? Because if we did a to the power of negative 2, that's 1 over a to the power of q. So didn't we already find out a product rule? Didn't we already identify a product rule? So how can I combine these into one exponent? What do you guys think? Yeah, thanks, Pranay. Thanks, Nihira. Absolutely, it's a to the power of p minus q. Absolutely correct. Yeah. So this is kind of like where this division rule comes from. So I believe if you understand the product rule and you understand negative exponents, you don't really need to memorize this quotient rule, this division rule, because you can kind of just bring it up from there. Okay, so now that we have this quotient rule, let's talk about zero exponents. So you've seen negatives, you've seen positives, but you haven't seen me write a zero. That's for a reason. Let's take a look. Anyone got any guesses? What is 2 to the power of 0? 1. Very good. What about 3 to the power of 0? Also 1. Interesting. What about 5 to the power of 0? 1 again. Okay, that's pretty crazy. There must be something up. Let's take a look. Let's actually look at this quotient rule, all right? Let me find a dark blue. Okay, let's take a look at this quotient rule. I have a to the power of p minus q, right? So if I have 2 to the power of 0 and I want to express it as a to the power of p minus q, I would have to do 2 to the power of maybe let's say 5 minus 5. I could do 4 minus 4, 3 minus 3, whatever. But let's say 5 minus 5, right? Because 5 minus 5 is 0. Now, I want to work backwards. I can do 2 to the power of 5 minus 5 is equal to 2 to the power of 5 divided by 2 to the power of 5, right? So what is that equal to? It's just 1, because I'm dividing the same thing in the numerator and denominator, so it has to be just 1. So like Nahira said, anything raised to the power of 0 is 1. Very good. Okay, the only exception to this is 0. So I'm sure you all know 0 to the power of anything is 0. But we just said that something to the power of 0 is 1. So what happens when I do 0 to the power of 0? What happens? Is it 0? Is it 1? Is it infinity? Is it 0.5? What could it possibly be? Okay, I see a lot of people saying 0, but the reality is that 0 to the power of 0 is undefined, because one would think that, okay, I have 0, I'm raising it to something, it should just be 0. But I also have that exponent of 1. Or I have that exponent of 0, so shouldn't that mean it's 1? And because it has two possible values, mathematicians don't define 0 to the power of 0. So this is kind of like a question. We don't really know what 0 to the power of 0 is. Now, you can definitely do some calculus, get maybe an estimation or something. Yeah, that's obviously beyond the course. Okay, awesome, awesome. All right, so we talked a lot about exponents. Let's go ahead and oh, just kidding. Really quick before we do that, one final rule. We talked about negative, positive, and 0, but those are all integers, okay? There's still one kind of other number for us to talk about, and that's fractions. So how can we do a fractional exponent? Well, let's take a look. But first, let me make that all smaller. Okay, let's say, this one I'm just going to go ahead and define because it's kind of hard to see. Let's say I had 2 to the power of 1/2. Now, when I have a fractional exponent, that actually represents a root. So because I have a 1/2, I'm taking a square root. So this is equal to the square root of 2. Now, if I had 2 to the power, or I guess I could do 3 to the power of 1/4, this would be the fourth root of 3. If I had 5 to the power of 1/3, that would be the cube root of 5. So whatever's in the denominator of the fractional exponent is going to be the root that I'm taking. Now, if I had instead done like 5 to the power of 2/3, that's equal to the cube root of 5 squared. Because I can write this as 5 squared to the power of 1/3. Okay, awesome. So that's just a little bit about fractional exponents. You do see this sometimes, especially when you're working with polynomials and stuff, so it's important to be familiar with the notation. All right, so I'm going to go ahead and give you guys kind of like a little summary sheet for everything we just talked about, in case that was just like crazy, oh my gosh, so much stuff, but I'm pretty confident most of you guys are quite familiar with this, which is very good. So let me go ahead, paste this over here. And so this is going to be everything that we just talked about. So let's go ahead and use this in a couple of problems, and then we'll move on and cover the last topic for today. Okay, awesome. So I'll give you guys a couple seconds to absorb that, and then let's go ahead and talk about, let's use this ugly brown, maybe. All right, let's go ahead and talk about some problems. All right, so our first question I have, oh, Aradi says pink. I don't know if I have a pink, unfortunately. Oh, maybe I can add a color. No, okay, I don't want to upgrade. Sorry, no pink. Yeah, no pink. Oh, I'm sorry. Okay, we'll use this ugly yellow-brown thing. Okay, let's say I have 6 to the power of x, and let's say this is equal to 34. Can you guys tell me what 6 to the power of x plus 2 is? What is that? Wow, Monique looked really excited. Okay, Monique says 1, 2, 2, 4. Anyone else got something similar or different? Okay, Sharanya also says the same. Divyan as well. Radhya. Okay, seems like we've got a little bit of a consensus here, which is good. All right, so first you must be looking at me crazy because you're like, okay, isn't 6 squared 36? Like, what power could 6 possibly be raised to get 34? I don't know. I don't know. And that's the truth. And so you'll notice it doesn't actually matter what x is because we're looking for 6 to the power of x plus 2. And using our exponent rules, we can say that 6 to the power of x plus 2 is 6 to the power of x times 6 squared. And don't we know each of these values? We know 6 to the power of x is 34, and we know 6 squared is 36. So if we multiply this together, we can use difference of two squares to get 100 or 1,224. Awesome. And if you're interested in seeing how we did this really fast, we actually have a number sense class where we kind of go into this in depth. So if you want to go check that out, that is available for you guys. Yeah. Okay. So as you can see, there's lots of questions in exponents where you may not know the actual exponent, and that's totally fine because you don't have to know the exponent. You just need to use the values you're given. Okay, awesome. Let's go ahead and do a couple more examples. All right, let's say I had 4 to the power of x plus 1 is equal to 2. Can you guys tell me what 4 to the power of x minus 1 is equal to? Awesome. Parth, if you were asking about what this is called, this technique is called difference of two squares. Awesome. Okay. Manit says 1 over 8. Awesome, awesome. Any consensus? You guys agree, disagree, partially agree? I don't know, maybe you have the same numerator and then a different denominator. Okay. Arush, Aranya, Sarah, Aradia. Okay, awesome. I realized this class had a lot of A names, which is really interesting. I think that's cool. But it's I know it's gonna trip me up because I might say someone's name wrong, but that's okay. All right, so I see a lot of people saying 1/8, and I would agree with that. The reason why is because we can say that 4 to the power of x minus 1 is equal to 4 to the power of x plus 1 times 4 to the, oh, that x looks kind of like a multiplication, times 4 to the power of negative 2. Because if we do x plus 1 plus negative 2, that gives us x minus 1. So basically what we're doing is we're doing 2 times 4 to the power of negative 2 is 1 over 16. So 2 times 1 over 16 is 1 over 8. And that's our final answer. Awesome. Okay. Oh, I think this one's a challenging one. Let's do this one. Let's do like 2 more examples and then we'll go ahead and move on. All right, I don't like this ugly yellow anymore. I like this, let's do a dark, like a violet. I don't think we did that yet. All right, okay, actually, how many digits are there in 2 to the power of 2001 times 5 to the power of 1950 divided by 4 to the power of 27? What do you guys think? Vivian is like question mark, question mark, question mark. What the heck? Yeah, so if you've been getting off so far using calculators, your calculator is gonna crash out on this question. So I would warn you, don't use a calculator. But that's okay. You can definitely do this without a calculator. I promise you, it's possible. Yeah, you must be like, okay, what do I even do? I have a 2 to the power of 2001. What the heck? Okay, let's take a look. Oh, Manit says 1950. Okay, Arav also says 1950. Okay, cool. So we have some answers. Let's see if we can verify that. Okay, so to start off, I don't really like fractions. I kind of want to get rid of that nasty denominator, so let's do that. My only problem is it's a base of 4, and I don't have a base of 4 in my numerator. But I do have bases of 2 in the numerator. And I know 4 is a power of 2. Can you guys convert 4 to the power of 27 to a power of 2? Okay, Manit says it's 2 to the power of 54. Do you guys agree with that? Disagree? What do we think? Okay, Pranay also says 2 to the power 54, so does Aditya. Okay, and that's correct because 4 is 2 squared. So if I'm doing 2 squared raised to the 27th power, remember our exponent multiplication rule, I get 2 times 27 in the exponent, which is 54. So 2 to the power 54. So this expression is 2 to the power of 2001 times 5 to the power of 1950 divided by 2 to the power of 54. Okay, can I maybe simplify this part of the expression? Hold on, let me do blue. Is it possible to simplify that? What do we get? In this case, we should use our division rule. So if we use our division rule, what values should we get? Okay, Manit says 1947. What do you guys think? Does that sound about right? It's not impossible. We're like halfway there. Yeah, keep sticking it out. We're almost there. Okay, Araf says 2 to the power of 1947 as well. Yeah, I agree. So if I have 2 to the power of 2001 divided by 2 to the power of 54, remember that's just our division rule. We've seen this already. I'm just going to do 2 to the 1001 minus 54 to get 1947 as my exponent. So this finally becomes 2 to the power of 1947 times 5 to the power of 1950. Okay, so we still have like ginormous exponents, but we no longer have a fraction, which is good. It's really good. Now, what I'm going to do a little bit of fun grouping. I'm going to do 2 to the power of 1947 times 5 to the power of 1947 times 5 cubed. Now, do you think I can group this into one exponent? What do you guys think? Yeah, okay, like Manit says, we can actually combine this by multiplying the two bases together. Okay, and also Varad kind of agrees. Yes, so what we do here is because the exponents are the same, we can do this is 2 times 5 to the power of 1947. Now I can only do this because the exponents are the same. If I had 2 to the power of 1948 times 2 to the power of 5 to the times, oh sorry, hold on, let me say that again. If I had 2 to the power of 1948 times 5 to the power of 1947, then I couldn't just multiply the bases together because they have different exponents. That's why I separated this into 5 to the power of 1947 and 5 cubed. Because I can't just multiply 2 and 5 when they have different exponents originally. So as you can see, I have 2 to the power of 5, or 2 times 5 to the power of 1997, or 1947. So this becomes 10 to the power of 1947. And what is 5 cubed? It is 125. Excellent. And so in total, I have a bunch of zeros, and then I have 125 at the beginning. So I have precisely 1947 zeros. And then how many non-zero digits do I have? Well, I have 3 because 125 has 3 digits. So if I add those together, I get a total of 1950 digits. What do we think? That was a bit of a roller coaster, wasn't it? But were you able to see how even though we had really large exponents, we didn't really calculate this full value. We didn't put in any divisions or use our calculator or anything. We were able to do some clever factorizations and some clever simplifications to get some large power of 10 multiplied by some itty bitty power of 5. So that's how we were able to simplify this question and find out they were 1950 digits. And if you had, okay, first of all, your calculator would crash if you tried to do it on the calculator. But second of all, or actually, you know what? It might express it in scientific notation, but I'm not quite sure. And then second of all, if you did it by hand, you would be sitting here for ages multiplying it out. Okay, so Pranay actually raises a good question. Pranay, remember we're doing multiplication, right? So I would have 1 like followed by 1947 zeros. And then if I multiply this by 125, this 1 gets replaced by 125. So instead I have 125 at the beginning, and then I have the 1947 zeros at the end. So it does match up to be 1950. Okay, excellent. All right, so I think that's probably the most challenging question. So let's go ahead and move on to our new topic, since I think you guys, yeah, Devian says the calculator crashed it. Yeah, don't use calculators for a question like this. Yeah, so I think you guys have got a very good handle of how this works. So let's go ahead and try out a couple of new topics. Let's do one last new thing. So, we talked a little bit about fractional exponents and we talked a little bit about those square roots and stuff. So I want to do a little bit of work with the square roots. But first, let's clean up the screen. Okay. All right. Lots of random numbers out and about. Okay, awesome. All right, I'm going to leave these exponent rules in case anyone is interested in keeping them. Alrighty. So we call fractional exponents radicals. So those square roots I was writing earlier, those cube roots I was writing earlier, those are called radicals. Pretty rad, I think. And so these they're kind of the opposite of exponents. So subtraction is the opposite of addition, division is the opposite of multiplication, radicals or roots are the opposite of exponents. So basically, uh, let's see. Yeah, okay. So let's say I had the square root of 9. This is basically trying to tell me like what number when I square it gives me 9. So this is kind of like the opposite of that, if you can make sense of that. And Vivian, yeah, that's actually equal to 3. Now, some numbers you can't always simplify. Like there is no integer square root of 2. There is a decimal version, but there is no integer. And so that's why I kind of just leave it as square root of 2. Like Vivian says, we call numbers like that irrational. But square root of 9 is not irrational since there is an integer cubed or an integer squared that gives me 9. That integer is 3. Excellent. Now let's say I had cube roots. Can you guys find the cube root of 125? What could that be equal to? 5. Excellent. That's because 5 cubed is 125. So the cube root of 125 is just 5. Very good. And so just like there are square roots and cube roots, we also have fourth roots and fifth roots and sixth roots and so on. So lots of different roots. Oh, whoopsies. Okay. So let's talk a little bit about some properties of radicals. Now, the nice thing is you guys have already dealt with a lot of exponent rules. So radical rules really kind of just repurpose exponent rules because all the radicals can be expressed in terms of a fractional exponent. So to start off, let's say I have the square root of a times the square root of b. Can you guys predict what this might be equal to in terms of a and b? What do we think? Yeah, the square root of a times b. Very good. And the reason why I know that, because I can write a to the power of 1/2 times b to the power of 1/2, and because these exponents are the same, I can merge their denominators together to get a times b to the power of 1/2. So that's how I get the square root of ab. Very good. Now, similarly, I have the square root of a divided by the square root of b is equal to what? What is that equal to? It's kind of like related to this actually. So really like, even if you didn't know that first rule, you should definitely be able to figure out the second rule. Yeah, it's the square root of a divided by b. Yeah, it's pretty similar to how we prove the division rule for exponents. We're literally just repurposing that. And then one final thing, let's say I had, um, hmm, let's say I had the square root, or let's say I had the nth root of a, um, no, hold on. I don't like that. Okay, let's say I had the square root of a to the power of n. I can rewrite this as the square root of a to the nth power. So this is kind of just a way of rewriting it, but it can actually be pretty useful sometimes. So yeah, that's just another fun thing to remember. All right, now one thing that comes up a lot, if I'm taking the square root of a square number, so let's say I'm doing the square root of 9, you might be thinking like, okay, I know that negative 3 squared is also 9, right? So why do I not write -3 squared? Well, the convention is that whenever we are finding the square root of a perfect square, we always take the positive number. So we don't write -3, we write 3. Yeah, so whenever I take the square root of a perfect square, I always write the positive result. Okay, so then let's finally talk about how to simplify radicals. So to simplify radicals, I want to pull out as many perfect square powers as possible, and then I want to leave any remaining factors under the radical. So for example, if I had the square root of 125, what would that be equal to? Careful. So 125 is actually not a perfect square. It's actually 5 cubed. So I would pull out that 25 part because 25 divides 125 and it's a perfect square. So the square root of 25 is 5. But then I'm left with an extra 5. I have that square root of 5. And since 5 is prime, it's not a perfect square. There's nothing for me to simplify. So like Arav and Devion said, the square root of 125 is 5 root 5. Awesome. Now, can you guys tell me what the square root of 48 is? Yeah, so a Hanukkah, basically, we're just trying to simplify a couple of radicals and get them in their simplest form. Well, I can write 48 as 3 times 16, and 16 is a perfect square. It's actually 4 squared. So I can write this as 4 root 3. And that's how I simplify radicals. So the idea is to pull out your square root factor and write that, and take the square root of that, and then write whatever is remaining. And whatever is remaining should not have any more powers for the root. Okay, awesome. So it's getting close to 9 o'clock, which is when we end. There are a couple more topics to do, but I'm not going to introduce them just yet because they can be a little tricky and I want to make sure we have enough time. So for now, this is the end of today's class. I want to thank you all so much for joining me today and sitting through this and taking some time off your spring break to do some math with me. I had a lot of fun. I hope you guys had a lot of fun as well. But if you have any questions or concerns or anything, please do let me know. If you thought that today's lesson was a little easy, I like to start off on the easier side, and then the lessons do get a little harder. So after this lesson, next week we'll be doing a little bit of word problems, systems of equations, stuff like that. So if you're interested in that, do come back. We would love to see you guys. But yeah, until then, homework will be released, and hopefully you guys have some fun with those problems. So thank you all so much once again, and enjoy the rest of your spring break. Bye, everyone. As a reminder, we will not have class on April 7th, I believe, 6th, the next Sunday, because of spring break, but we will have class after that. There'll be a reminder email, though, so don't worry about that. Okay, wonderful. Thanks, everyone. Bye. Have a great evening. Awesome. Bye, Ditya. Thank you so much. Bye, Kenzo. Thanks for coming. Bye, Adyak. Wow, that's a long wave, Kenzo. Awesome, awesome. Alrighty, I'm gonna go ahead and end the Zoom meeting. Thank you all so much once again, and have a great afternoon.